All right, so what questions do we have? Anything at all?
I don't think I have any like specific questions
Okay.
right now. I think just maybe like can we go through a practice problem?
Sure.
From the
Of
Tomasi?
what kind do you want? Like spectroscopy or radicals?
Um, yeah, I think where I go have trouble with, like especially in the Tomasi worksheet, and I think it might just be that I have to memorize this.
Okay.
But like looking at the IR table and trying to figure out what I see from that, and then how to like put that
Mhm.
back into the mass spec and then use that to find a formula. Because I know we do have to look at the IR and relate that to the mass spec to come out with a formula, correct?
No, you do not need IR to come up with the formula, thankfully.
Oh, really?
Yeah, so
How do
here,
we see
let's
the
just quickly
nitrogen?
go over this again. So, I mean, IR can be helpful, but you technically don't need it for the formula. So, determining... Matt, I know you keep like disconnecting. Are you good?
Yes.
No, I meant Matt, the
Oh,
other one
oh,
in here.
sorry.
Sorry, yeah. Nope, he's gone again. Okay, well, we'll just keep going. Determining the formula. I think he's having trouble unmuting himself, and that's why he keeps disconnecting. So we'll see. So what we really need here are kind of some data points. So we need the mass to charge ratio, the m over z, which is our molar mass, really. That's going to be the big part here. M plus 1 will tell us the numbers of carbons, and then M plus 2 will tell us the number of chlorine or bromine. So those will, that's kind of all we need to really focus on. I'm not going to throw any M plus 4s at you, anything like that. That would just be over the top. So um, just since I saw Matt come back in, the mute button is on the bottom left. I don't know if that's like what you've been disconnecting and reconnecting for, just so you know. Okay, with the molar mass, let's take one at random. Do you have your Tomasi set kind of on hand?
Yeah, I have it right in front of me.
Cool. Take a problem at random. Let's do one with an odd number. If you want to find some Tomasi set that has an odd number molar mass. Let's do that as an example.
Through it right now. Trying to find one that I haven't done
Okay.
that has an odd number. Oh, 25?
Okay. I will actually have to pull this up. So in the meantime, why don't you tell me what's the
I think
what's
like when I
yeah.
look at molar mass, I think or mass spec, I think the one trouble I'm having is how do I know if there's nitrogen in it? Like if I don't look at the
Yeah.
IR.
All you need to know is if there's an odd number or not.
So always if there's an odd number, just always assume that there's nitrogen in it.
There will be one or three or some odd number of nitrogens. Yes.
So how do you know how many nitrogens there were?
I'm not gonna give you an even number of nitrogens. So
Okay, so it'll always be like 1 or 3.
yeah, and 3 again is kind of overkill as well. So if there's a nitrogen, at least for now, it will just be one nitrogen. So
Okay.
and that will be your hint, is that it's an odd number. So let me pull this up. Which are you looking at, like Tomasi set 1 or set 2?
I think it's set 1. Problem
Okay.
25, the mass spec on it says 175 AMU. If it's the same one.
23. Okay, I think it is set 2 because 1 apparently only goes to 23. So.
Oh shoot, sorry.
No, you're good. You're good. 25, yes. So 175. Alrighty. Oh, how curious. Oh, this is going to be a kind of a pain of a problem. But, ew, and what is this IR? Oh, that's terrible. Okay, well, anyways.
I have the IR on it too.
Let's see. Okay, so when we take a look at these, this one's going to kind of be a giant mess because we've got some halogens in here. But we can go ahead and give this one a shot, although it is going to be a tricky one. But we can go ahead and do it. So All right, so when we take a look at the molar mass here, can we? I'm sorry, let's just do one without the halogens, because the thing is, chlorine can kind of mess with our normal odd being the nitrogen molar mass kind of thing. So, do I want to? So, because there's going to be, we're going to see there's quite a few chlorines in this, that's actually going to throw off our normal odd thing. So, are there any other odd number ones? We can do this one after, but this one will kind of be an exception because it's got the n+2 peaks and n+4 peaks that are pretty important here. And remember, I said I'm going to kind of avoid n+4 for us on the exam.
No worries. I'm looking through it right now. I think they're...
Did you do number 6 out of curiosity?
5. Yes, I did. I started it. I was able to get all the way to the... I'm having trouble creating the structure too, so I got all the way to the structure part and couldn't put together the structure.
Okay. Let's just do that one for now, and then we can kind of work on that structure. So what number did I say this was? 6. Okay. Just because when you have halogens, it's really going to mess the normal things up. Okay, so we've got our molar mass. We're working on problem 6 here. Set 2 and number 6. All right, so we have our n+1 is 7, and our n+2 is 0.6. What's the first step with coming up with a formula?
Taking the n+1 and dividing it by 1.1 to find how many carbons.
Right. Right. And so in this case, that's going to be roughly about 6, right? I don't really have a calculator on hand, but it should be fairly close to 6. Right?
Yes, it was 6.
Cool. Awesome. So that means we can go ahead and subtract the, we know we have 6 carbons, right? So we're going to need to subtract their molar mass from the molar mass of our compound. So we have 6 times 12, which is 72. We'll subtract that from our molar mass. This is from the carbon. And that's going to give us, what, 51?
Yeah, 51.
Cool. So, without any other data, the one thing we do know is that we have an odd number, right? And so, kind of the hint that I've given us here is that odd numbers are going to tell us that we have nitrogens in our molecule. So molar mass of nitrogen, we should just go ahead and subtract that because we know there's going to be a nitrogen in this because it's an odd number. Again, don't worry about number 25 because that one's going to have multiple halogens because of the n+4. We're not going to have that on the exam. That's too... I don't want to give contradictory information. So let's subtract the nitrogen that we know is there. So nitrogen's molar mass 14. 37 is left over. Yes. Okay, so with that, we have 37. Is that, are we kind of done right now? Or do we still have more to go?
No, I subtracted oxygen twice. And then
okay. Right, so because if you do it, if you do it the first time, you get 21, which is way too many. So you need to do it again. And so that'll give you 5 at the end. So the formula for this could be then C6H5NO2.
Yes.
Okay, so that's how we're going to find the molar mass with the nitrogen. We just do this because it's odd. So we're going to subtract the 14 from it first. Okay, so with that, now we can actually go ahead and look at the spectra here. Oh no, we should do the IHD. So that's just the formula, right? So we've got number of carbons plus nitrogen over 2 minus H over 2 minus X over 2 plus 1, or whatever. I don't know which formula he's kind of given you for this, but you'll do your formula, right?
Can I ask you if my formula is correct? I think it's
Sure.
the same thing, but I have 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens all over 2.
Plus then? What about nitrogen?
Oh, plus nitrogen, yes.
Okay, yeah, it's the same thing. So mathematically, these are all like 2C over 2 and over 2. Yeah, they're all the same here. So, yep, that'll work just fine. Okay, so let's go ahead and do it. So 6 plus half minus 5 halves plus 1. Let's see, that's going to be minus 4 halves is 2. 6 minus 2 plus 1. I can't do this simple math. Let's see, 5? Yes. Cool. All right, so we've done the kind of base work for this now. So were there any problems getting to this point? I know you've kind of already started piecing together the structure here.
Yeah,
so,
this I was good with. And then I just took the IHD from that. I just assumed like, oh, we must have a benzene in it because the IHD of 5 is pretty high. So
it's super high. So it is a very good. And if we also look at the NMR, we see a lot of stuff around 7 and 8. So yeah, that's pretty indicative. We've got benzene going on here. As well as if you look at carbon NMR, we've got everything between 100 and 150. So again, that's pretty strong evidence that we've got benzene.
Fair assumption. Sorry to interrupt. Is it a fair assumption, just like when you do have an IHD of like 5 or above, that there will be a benzene, or should I just not make that assumption and still look for like double bonds and triple bonds?
I mean, it's generally safe.
Okay.
Generally, of course, there may be exceptions, but generally, I mean. Thankfully, aromatics are fairly easy to see in both hydrogen and carbon NMR, so your assumption can be very easily just checked. You can say, okay, do I have carbon peaks in the right area? Do I have proton peaks in the right area? Okay, yes, all the evidence points here to having a benzene. So, yeah, I think that's a good place to start. And then just, look at the rest of it and be like, oh, wait a second, no, this doesn't make sense with the benzene. So, okay. Cool. So, we have our benzene now. Thankfully, that's all of our carbons, right? So, that's great. That's pretty strong information. And honestly, with 5 hydrogens, like, once we've figured out it's a benzene, we kind of have very little left to do. But we should be thorough and investigate everything. So let's take a look at the IR. Do we see anything kind of useful here?
I didn't notice anything because there's nothing in the 700.
I don't see anything
and
either.
In 3300. And nothing in 3300.
Right, nothing in either of our kind of main 2 locations. So great, IR is done. All right, NMR we have. If we want to we should get in the practice of kind of coming up with a table of everything here. So we've got something at, I don't know, what do you think that first peak is?
I said around 7. Oh, that would not be 7. Oh, 7.5. That would not be 7. Oh, 7.5.
Yeah, 7.5 or so, I'd say. Yeah. And then we have another 7.7 or so, and then 8 8.2?
Yeah.
Okay. These are kind of all aromatics, so we don't really rely on the splitting as much necessarily. So it's kind of just, I don't want to say just, glob them all together, but we can kind of glob them all together. But if we were good, we would look at the integrations. We see that 13 is our lowest number, and the other 2 are just multiples of 2 of 13. So we can say that the first one is 2H, 1H, and 2H, which makes sense. We've got 5 hydrogens. And we see that we have in our carbon NMR, we have kind of 4 peaks. That one at 147 or 148 is quite small, but it is technically part of our spectrum. Don't worry, mine are going to be super clear because they are computer generated, so they just use algorithms to generate the spectra. So great. So we're going to want to do that. We don't really need to worry about multiplicity for aromatic peaks. Normally we would indicate, doublet, triplet, all that good stuff, but we don't need to do that here because aromatic splitting is nasty. And then we can go ahead and see. So we have all of these aromatic hydrogens. We have no indication that we have either an alcohol or an amine in this molecule because we did not see those in IR, and we also don't see those in the NMR, right? We would expect, if we had an amine or an alcohol, we would expect those pretty upfield, right? Compared to these, we'd see them around 3 or 4 or 5, and they'd be kind of broader peaks in the NMR. So we don't seem to have any amines. So, if we just have NO2 left over, we know that's a functional group, right? So chances are we can just let's just throw it on the benzene. because we know we've got 5 hydrogens on there, and we just need somewhere to deal with this NO2. We have one IHD left that we haven't really talked about, and we know that NO2 has a double bond as a functional group, right? So, let's see, let's draw it out. So this one, it's kind of, what would be the best way to describe this? It's kind of looking at what's not there more than what is there, if that makes sense. Like, we didn't see any evidence of alcohols, evidence of OH or NH, right? We saw none of that, right? And it'd be weird to be like, you know, to try and do something where we like put some O's here and connected them with other O's. I don't know, like that's just not generally, these will be pretty like normal structures with functional groups that we recognize. Like, you would probably not see a peroxide in them. So kind of with this one, it's because we have no evidence of any of these other functional groups, we're just going to put all the 5 hydrogens on the benzene and just throw everything else in there. All right, I mean, there are other ways to assemble this. We could put the oxygen connected to the benzene, but that's less common. Normally, we have the nitrogen as a nitro group. That's pretty common. If you were to put this, however, you know, this technically is a valid structure. Like, I would accept this as an answer. Although it is less common. This is not a normal functional group you see on benzenes, but technically, if you arrange them this way, it would still work with the data we have. Because there's no carbons or hydrogens as part of that nitro group, or the NO2, whatever form it happens to take, so that would be okay as well. So, I mean, that's the thing, is sometimes we'll end up with multiple structures that might give the same spectrum. Or at least one that would be you would not be expected to distinguish.
Thank you.
So I know it's kind of not helpful to say like it's just what's not there, but maybe that's another tool that you can add to your kind of toolkit here. Out of curiosity, have we taken a look at some of the practice exams for spectroscopy? Let me see if there's any good ones here. Let me see if we have a good problem here, because this will be kind of closer to what you're going to have on the exam, because the spectra will look like these. If that makes
on the
sense.
exam, we're going to be expected to create the formula too, right? We're not going to be given the formula.
Yes. You'll be given just like
okay.
this sort of stuff.
Yeah.
Up here. Mm-hmm. And so, again, I'm telling you right now, if it's odd, just do the nitrogen. Don't worry about other things. The reason that it's going to be weird is because on number 25, there are 2 chlorines in there, and that's going to mess with us. So I wouldn't worry about that. Let's take a look at, why don't we do, just looking at her practice exams real quick. Oh, gosh, that's kind of a pain. C14. Why does she give these crazy molecules? Okay, let's take a look at number... I'm looking at, if we go to Mrs. O's website, we can look at, I'm looking at exam fall 2018 on problem 7. Here, I can put the link in Discord for you so you can just quickly get there. Let's take a look at that one. We can take a look at number 7. So maybe it's one that you've not seen, so like all of us are kind of in the same playing field here. So, and that way I can show you kind of exactly what I'm looking for when we answer these. And then you can also see what the spectra look like. So, although this is going to be, it's a big molecule again. She really loves those. But we can work with it. All right, so have we all pulled that up? All right, let's see. So let's go ahead. Yeah, go ahead. Were you going to say something?
Sorry, did you put the link in the chat?
All right.
Sorry, did you put the link in the chat?
Oh, okay, I did, yes. It's in the questions section, yeah, because I'm just randomly posting things, yeah. So I'll go to that one, and then the last page, number 7. And that's what we're going to look at. So again, this is kind of a nastily giant molecule. This is going to have quite a few carbons, so it'll be more than I'll give you, but it will still be good practice because this is a harder problem. All right, let's take a look. So this is Fall 18, number 7. We have a molecular ion peak at 214. We have an M+1% of 15.1. And then we've got the spectra. So let's go ahead and deduce the formula first. So even number, that's a good thing already. We have some information we can get from that. Let's go ahead and find out how many carbons we have. And remember, we just divide by 1.1. So what do we get there? By the way, don't forget your calculators for this one. What do we get? Anyone at all?
Sorry, it's 13.7.
Sorry, it's 13.7.
Thank you. Okay, so let's 13.7 really? Okay, let's just let's assume 14. Although that is okay, I have not given you any that don't round like clearly like 0.9 or 0.1 or something. So at least that might set us back, but we'll work with 14 for now. Just so you know, Matt, I saw you unmute. I still can't hear you. That's okay. We'll work with it. So 14. 14 times 12. Let's just have Alexa do the work for us. Computer, what's 14 times 12?
14 times 12 is 168.
Yeah, 168. Computer, 214 minus 168. Come on, you guys. Ow. Computer, 214 minus 168.
214 minus 168 is 46.
46, okay. So, let's see, with 14 carbons, this is still unreasonable, so let's try getting rid of some of this molar mass with some oxygens, right? Let's try one and see what happens. Gosh, this is going to be kind of a pain. So we've got 30. Is 30 a reasonable number? It is technically, right? C14H30O. That's a possibility. You guys are so lucky you don't have her for this. Just because this seems like we have... that would be a pretty boring molecule because it would have an IHD of 0. I'm going to say that's not it, just based on the fact that if you look at the spectra here, we definitely have stuff like in proton, we've got stuff at 6 and 7 and 8. We've got in carbon things at, greater than 100. In IR, we might have something at 1700 as well. So I'm going to say this isn't our formula, simply because the IHD of 0 kind of doesn't make sense here. Again, I'm not going to give you any sort of problem where you have to question it like this, but let's go ahead and question this one. So if we take another oxygen out, we're at 14. So C14H14O2. That might make more sense. going to be a giant pain of a molecule because that's going to have a very high IHD, but we can see if we can work with this. So again, I apologize that her problems are needlessly complex, but here we are. So IHD, let's do that next. So we've got 14 minus 7 plus 1, which is going to be 8. Is that correct? It's 14 minus 7 plus 1, 8, yeah. Yikes. So, definitely I would say we've probably got a benzene here, right? That's a huge IHD. And if we take a look at the proton and carbon NMR, yeah, we've got things that would be appropriate for having aromatics. So, probably we've got a benzene in here. We've got a benzene, maybe. That would take care of 4 of them. Do we have 2 benzenes? Maybe, maybe not. What evidence do we have that we might not have 2 benzenes? And again, just throw things out. You know, anything that leaps out at you as maybe not doing it.
In this case, like when you're considering if there's 2 benzenes, would you look at the like IR, HNMR, and CNMR to like distinguish that, or like would you just look at the formula and look at how many hydrogens are in the formula to determine that?
Like would you just look at the formula and look at how many hydrogens are in the formula to determine that?
You know, actually, there's multiple ways. So probably I would look at the spectra first. Because, like, technically, like, if you've got, like, if we had some sort of, like, weird dibenzene thing, like, that would technically still be okay with the number of hydrogens that we have. And that would take care of all of our IHD. But if we take a look at some of these spectra, we may get a clue about what else may be there. That might help us determine if we have multiple benzenes or not. So, like, for example, let's look at IR. Do we see anything kind of important in IR?
Is that a peak at 3,300 or? Oh. Okay.
Is that a peak at 3,300?
I don't think it is. Because we only have oxygens in this, if there were an alcohol, it should be very big and very broad. That looks like a little pointy, and I'm going to say that's not kind of going to be important. Just because of how small and narrow it is. Usually alcohols are very broad peaks and very large peaks.
It looks like there's a peak at 1,700.
Anything else in the IR?
It looks like there's a peak at 1,700.
I see that as well, and I would agree with that. So, because of that, because IR shows us that we probably have a carbonyl in this molecule, that tells us we can't have 2 benzenes. Right? Because each benzene needs 4 IHD. If we need 1 of the IHDs for a carbonyl, then that means we only have 7 left.
That
which
makes
means
sense. So
we can't
look at
have
the
2
IR
benzenes,
to determine
right?
that.
That makes sense. So look at the IR to determine that.
Matt has suggested there may be a terminal alkene or alkyne that might be on the left of the CH stretch. I need to kind of zoom in on this because it's really tiny. Don't worry, my spectra are on 2 pages, so you can see kind of a little bit more. It's kind of hard to say, Matt. There might be something right there at like 3050 or so, or 3100. It's kind of hard to say. However, if we look at the Proton Nmr, we see those 2 peaks, or like D and E are kind of around 6. That's pretty indicative of an alkene. So we probably will have an alkene somewhere in this molecule, I would agree. So that would be another way for sure. So I that could definitely be there. Okay, but again, I would not rely on IR for alkenes, just because they can be kind of globbed in with the regular CH peaks, and it can be hard to see those. So. Okay, so let's move on from IR right now. We just see we have got a carbonyl. Maybe something else. But that's okay, because IR is the least useful of our spectra. Let's go ahead and now we've got 1, 2, 3, 4, 5, 6, 7, 8 peaks on Proton Nmr. We've got peak A, B, C, D, E, F, G, H. Because again, she loves these sorts of molecules. Let's go ahead and write out all of our chemical shifts and the multiplicities, as well as the integrations. So, chemical shift for A, what will we say? Maybe like 8.1, thereabouts? And
it's a doublet,
what's the shape and
the integration is
for that?
2.1.
It's a doublet.
Mm-hmm.
Oh, divide
And the
it.
integration is 2.1.
Right. But if we like
Divided.
divide, right? I mean, hopefully these are pretty.
It's gonna be 2.
Pretty normal. They should be pretty easy, these hydrogens. So.
It's gonna be 2.
Yeah, it's just 2, right? I would say it's 2. Cool. Great. So we've got a doublet of 2H somewhere at 8.
B, it looks like around like 7.3.
What about B there?
And then
B, it looks like around like 7.3.
Mm-hmm.
Yeah.
Somewhere like it's between like 7.3,
I would say
7.5,
it's
kind
a
of
quartet.
is a broad set, isn't it?
Yeah.
Okay.
I would say it's a quartet.
Now, interestingly, I would say that's not a quartet. Why would it not be? Because quartets, if you remember, quartets have to look like this. If you can see my screen, remember that quartets have that kind of 1:3 to 3:1 ratio.
Yeah.
So
Would you say
if
it's
that's
2
not it,
doublets?
what else could it be?
Doublets. Okay.
Would you say it's 2 doublets?
It's a doublet of doublets, right? So that's also some indication we've probably got an alkene in here, because that's when we start getting these weird splitting patterns. And it also says that it's unusually de-shielded, meaning it's farther to the left than we would normally expect it. So that's what that means, by the way.
I'd say that's exactly
okay,
like
let's
7.
move on. What's C? What's the chemical shift for C?
I'd say that's exactly
Doublet?
like 7.
Yep, pretty good. 7.0, and that is
He was
doublet, I would
1.
say. And I'm sorry, we forgot the integrations on B.
He was 1.
Oh yeah, 1H, and then this one's just 2H again.
Right.
How
D, I would
about
say
D?
it's around like 6.4.
D, I would say.
And is that a doublet of doublets
around
again?
6.4.
Mm-hmm.
And is that a doublet of doublets again?
Gosh, I'm really zoomed in. It does look like a doublet of doublets. Kind of, but they're very close together. Because this is kind of unclear, let's just put this as D or DD. Just, if it's going to be a doublet of doublets, they seem to be very close, so it might be something geminal, where it has that very small, different coupling constant. Like, where B, they're all spread out, so that's probably like a cis or trans along a double bond, but D, if that is a doublet of doublets, it's probably a geminal one, meaning it's 2 on the same carbon or something. But we'll see. Let's see what happens, because remember, geminal ones are a pain. Let's just keep moving on. Let's leave it as this for now and
like
keep
5.7.
going. So 1H, and then what's the next one?
Yeah, I would say like 5.7.
5.7, and again, it kind of looks like it's one or the other. If it's a doublet of doublets, then it's geminal, and that would make sense that both D and E are 1 hydrogen. If they're geminal, that means they're on the same carbon, and so that could be why we see both of those have that kind of itsy-bitsy splitting. But let's worry about that later. All right, thankfully now we have got some normal
F
peaks
is like
down there
2.5,
at the upfield
and I would
side
call
of
that a
things. So
triplet.
what do we got next?
Yeah,
And
F
then
is like
F has an
2.5,
integration of 2.
Mm-hmm.
And then G, I would say about 1.7,
Uh-huh.
1.7 maybe.
And then G, I would say.
And then
about
it's a 5 is
1.7
keen.
maybe.
Oh, so this is 6. Sorry, 6.
And then it's a 5 is keen. Oh, so this is 6.
It's
Sorry,
6, right? Yeah. And you can tell by the way if it's even or odd,
Oh, that's
depending on
even,
like
got
if
it.
there's 2 peaks that are the same size in the middle and kind of like
Okay.
symmetrical that way.
that's
And then
Yeah, like
H
odds will have just 1
is
peak in the middle.
1.1 and
Okay.
triplet.
And then H is 1.1.
It has an integration of 3.
Yes. Triplet and then 300 is
It
great.
has an integration of 3.
Right. Okay. So, goodness gracious, let's see what we can do with this. Where do we want to start with this? So we see that there's aromatics. We probably have some alkenes in here as well. And then we've kind of got some just plain old regular aliphatic stuff. We can start anywhere and kind of just experiment based on some of these things. Like, we would probably say that like A and C are probably going to be aromatic, right? Do you remember what kind of special pattern that is for A and C?
I
out
don't.
of curiosity? Like, it's a case of something special.
I don't.
Okay. Anybody else out of curiosity? I don't remember if I mentioned it in the videos or not. And I'm not sure if he has mentioned it in class either. But I'll tell you. So, if you see aromatic peaks, by the way, I'm kind of ignoring B as aromatic because that note says it's extra deshielded, so I'm going to say that's not aromatic. Plus, also, it's a doublet of doublets, so, like, it's not aromatic. So, A and C are aromatic, probably, given their chemical shifts of 7 and 8. If you see a pair of doublets, not a doublet of doublets, but two doublets that are aromatic, that are kind of far apart from each other, that's pretty indicative of what's called para-disubstituted benzenes. And that means, para, by the way, just means they're on opposite sides of the benzene. So, like, it would look something like this, where we've got them on opposite sides of each other. We would normally see then two doublets, and they'll be far apart from each other, because of the way the splitting works, because if you see there's only one hydrogen adjacent to each other hydrogen, so we're going to see them all as doublets. And we're going to see that, like, if we were to do these, A and B, or the A's would be equal to each other and the B's would be equal to each other. So if you have a special case like this, you would see therefore two doublets of 2H each in the 7 to 8 ppm region. So that's kind of a special case here. And I know Mrs. O loves to talk about that, so she's indicated that here. I don't think it's something I necessarily focus on too much, but if students going into this particular exam that we're doing right now would have that information, so we'll just work with that. Okay, so we've got two doublets of two hydrogens each in around 7 to 8 ppm, and we do see those. We have A and C that would fit those criteria. So I think we should probably go ahead and have that as part of our molecule. So I shouldn't put X's, by the way, because X's mean halogens. We'll put R's instead, because that's what we use in OChem. So A and C we can kind of take care of. With that aside, now we can work with stuff we do know, as a class at least. So with B, D, and E, for those, as Matt has pointed out, those are probably going to be alkene peaks. And how do we know that? How do we know that we have alkenes? Maybe in this molecule. The only time you'll see things like this, where we have the multiple splittings, like that, that's got to tell us we've got alkenes in here. So, we've got an alkene somewhere in this molecule, and we've got 3 hydrogens on it. And the fact that D and E have that kind of very subtle doublet of doublet thing going on, those two are probably right on the same carbon. And remember that geminal hydrogens on an alkene, meaning they're on the same carbon on an alkene, split each other differently. Like normally on a regular carbon, protons on that carbon don't split each other because they're equivalent. But in a double bond, they can. So, if that tells us we've got 1, 2, 3 hydrogens on this alkene, we probably have a terminal alkene. So that tells us we probably have an alkene in this molecule somewhere. And if we do that, we can try and guess which peak might be which. So when we take a look at these, those super subtle ones, D and E, are probably the geminal ones. Remember that geminal coupling constants are very small. They're almost the same as aliphatic, like 2 hertz or so. By the way, you don't need to memorize those numbers. Just putting that out there as well. So that's probably C and D. I'm sorry, D and E. If we look at that, D is higher than E. And we see that we have B, which is going to be the doublet of doublets there. The real doublet of doublets. And so, if we were to try and label these blue hydrogens, which one do we think will be B, D, and E? I'm going to label them just right now 1, 2, 3. Just so we can all talk about them together. Which one do we think is going to be peak B? And why? By the way, for whoever joined recently, we are looking at, if you go to Discord, the questions I put, the exam we're looking at, it's the Fall 18 exam for Mrs. O, we're looking at number 7. And Matt, you are correct in your messaging to me. The doublet of doublet indicates it for sure. So, when we're looking at this, we've got one very solid doublet of doublets, right? B is for sure a doublet of doublet. The other two are kind of iffy about. So which of these hydrogens is the most different from the others? One, 2, or 3.
The second hydrogen.
I would agree.
The second hydrogen.
Okay, we have conflicting information. I would say that this one is going to be 3. The reason for that is because if we look at the coupling constants, a cis coupling constant is what, about, about 12 or so? And a trans one is about 17. If we look at H2 versus the others, we would say that we've got, I'm sorry, this is about 2 hertz or so. If we look at it, HB is going to have the largest 2 coupling constants compared. Like between H2 and H3, we have 12 and 2. Between H1 and H3, we have 2 and 17. So, if we're looking at the splitting, we see that B is really split apart, which tells us that we probably have the bigger coupling constants there. So, I would go ahead and say, we could have, what's the word? We kind of want to look at the rest of the molecule, of course, first, but just looking at these with the kind of biggest difference in coupling constants, we'll probably go with H3 first. We'll go with that as our hypothesis, and we'll check it later on. And then we also know that between D and E, those are the ones that have the super close splitting. That would probably indicate that they've got this super small coupling constant involved there. And so, as a result, we can probably say that 2 and 1 will be the geminal ones, which will be D and E. As for which ones which, we probably need the rest of the molecule to work on that. But for right now, just because we'll just make some guesses. Why don't we put let's put one of them as D and one of them as E, and we will come back and verify these later on because we're not 100% sure about them. All right, so does that make sense with the alkene part? Alkenes are kind of tricky. So we chose this because it should have the biggest splitting. Of these. Okay. So now let's look at F, G, and H. What can we do with these? So F, G, and H, we have a triplet of 2 hydrogens, sextet of 2 hydrogens, triplet of 3 hydrogens. This is actually pretty... This is another kind of relatively common pattern. How might we arrange F, G, and H? What might that look like? We can take a look at the splitting as well. Like if it's next to 2H here, this one is next to 5H, and this one is next to 2H as well. Just based on the splitting, right? So with that, is there anything we might be able to kind of deduce? Anything at all. Just shout out ideas.
Would it be, I mean, G would be next to CH3, and then I'm assuming it would be connected to another carbon, like, so this would be more towards like the end of an atom, or end of the compound. I'm assuming it would be connected to another carbon, like, so this would be more towards like the end of an atom, or end of the compound.
I agree. So how might we arrange that? I agree that it's probably going to be somewhere towards the end of the molecule for sure. Why don't we take a look at this one? This will probably be the easiest one to analyze. H here. It's a triplet of about 1.1 with 3 hydrogens. What does that usually indicate? Or what might fit that kind of data? Let me copy this. What would give us a signal at about 1.1? Something really, really low. That would have 3 hydrogens. Indeed, right, a methyl group. Right. So we've got some molecule, and we've got a methyl group at the end. That's pretty indicative we have such a low... There's nothing else that would give such a low chemical shift of 1.1. It's a triplet, however, which means that there are 2 hydrogens next to it. So we know at least it's not just a methyl group out of nowhere. It's probably at least an ethyl group, right? We've got these hydrogens here. These are HH. That's convenient. Right. Matt, I would completely agree. So he's messaging me just because his mic is not on. So what we're looking at here is a propyl group, right? We have, with this, we've got here, this would be a sextet, because it's next to 1, 2, 3, 4, 5 hydrogens. This would be a triplet, because it's next to 2. And this will also be a triplet, because it's, well, presumably next to 2. Because, at least that we know of. So there's probably no hydrogens on this adjacent carbon either then. So that's what the splitting pattern would tell us. And if we look at the number of hydrogens, this would work as well, right? We've got 2 hydrogens, and 3 hydrogens. And then we're going to see that, okay, well, the only thing that's kind of not for just a regular propyl group is this 2.5 chemical shift, which tells us we just have something electron withdrawn nearby. So does this propyl group kind of make sense, how we got this? Generally, with things that are like kind of 3 or below, you can kind of just, they're all just going to be regular carbons that don't have, too much extra going on. And so, with this, let's take a look at our giant chemical formula again. It's C14. We know with our benzene we've taken care of 6, so we have 8 carbons left to deal with. With this alkene we've taken care of another 2, so we have 6 left. With our propyl group we have 3 left now to deal with. And we still have, we've still got this carbonyl and a second oxygen to deal with as well. So we're narrowing it down, and if we take a look at the protons, our benzene took care of 4 of them, our alkene took care of 3, so that's 7. Our propyl group has taken care of 2, 4, another 7, so 14, so we're out of hydrogens. So the only things that are left, we've got 3 carbons left. We have no hydrogens. We have a C double bond O here somewhere. We've got another second oxygen, which could be another C double bond O. We don't know that. And then what else do we have? IHD. We still have, 3 IHD? So, at this point, let's take a look at the carbon NMR, because we still don't quite know what's happening. We've still got 3 carbons to deal with. So, if we take a look at our carbon NMR, what is this? H-coupled splitting is shown. Have you talked about splitting in
no, I don't believe we have.
It's one of them kind of more advanced techniques for it.
No, I don't believe we have.
Okay, then let's not worry about them. So, 190. What does that tell us? And it's also unusually shielded. And if you see unusually shielded, that means it's too low. we would expect this peak to be higher. And again, don't worry, this will not show up on mine. I will not have this unusually shielded business. My things will show up where we expect them to. So let's just say it's going to be maybe like over here somewhere. What might that be? If it's like 200 or 200 higher, what would that be then for carbon NMR? Matt says aldehyde. Ketone or aldehyde, right? Why is it not an aldehyde? How do we eliminate aldehyde? Aldehydes do not have OHs. That would be a carboxylic acid that you're thinking of. We don't see an aldehyde because we would expect on Proton Nmr we would see something at 9 or 10. Singlet at 9 or 10 is your very strong indicator of an aldehyde. So because we have no singlet at 9 to 10 on HNMR, then it's got to be a ketone. Cool. And we already knew we have a C double bond O, but now we know it's a ketone. And this is always the fun part. There's always the and. Something in this, we have to think, where are we going to put this ketone then? Is there any information we have in our Proton NMR that tells us anything about where a ketone might be? How does a ketone affect our chemical shift? So Matt has written that, yes, there's no hydrogens on the C double bond O. That's a useful piece of information. It could give us singlets as well, but we don't have any more hydrogens, so we don't have to worry about that necessarily. But is there anything that we thought, okay, well, this can't be next to anything with hydrogens, or maybe there's something with chemical shift that might tell us where to put this ketone? Can we put it on the benzene? You can't attach a double bond to a benzene because you only have one place for bonding. Do you mean like adjacent to the benzene? Potentially. What evidence would we have to suggest that? Because there is something else here that does give pretty strong indication of something with a ketone.
The alkene? The alkene?
Yeah, we have that weirdly extra shifted alkene, right? Because normally you expect an alkene 5 or 6, right? So seeing a peak at 7.3, and again it does say there's some unusual, what is her word? Unusual shielding? Deshielding? Yeah, deshielded. Probably, we probably have it on that. So I would, let's take both your and Matt's information and put that together. So I would agree, we probably have it next to the alkene. And so we know that we have kind of no other pesky hydrogens to deal with. So if we do that, we've got this alkene now that's got the ketone with it. seems pretty reasonable. There are other options. Remember, this is still a guess and check process. Depending, unfortunately, because of 2.5 ppm for the F, which has 2.5 ppm, that could be next to a ketone as well. That's usually just about 2.4, 2.5. However, that's also where next to aromatic shows up, also where next to triple bonds shows up. So F could be a bunch of different things. So we could also have it like this. So, but because of that ketone alkene being extra, like we could have, not this one, I'm sorry. We could have our propyl group as well. That's maybe an option. So, good. We've at least figured out some places to put this ketone. Okay. So, we still have... I'm sorry, we have an IHD of 2 left, don't we? Not 3. Because we have the alkene and the carbonyl. So, we have this extra oxygen. We've got 2 more IHD left to deal with here. Do we see anything else that might be helpful for us? In the carbon NMR, let's look at that one. So we know we have our ketone, which is peak 1. We have, oh goodness gracious, how many others? We've got an alkene and an aromatic, which will give us 8 carbons. And I'm going to say those are all represented between that 100 to 160 area. Those appear to all be there. 1, 2, 3, because we've got some equivalent carbons as well. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. By the way, here's a hint. Because of the way the software we work, if you see those peaks 4 and 7 are twice the height of the other peaks on the carbon NMR, that's an indication that those are identical peaks. Like, it's kind of like an integration, like where integration tells you how many hydrogens of this type. Just because of the way the software works, peaks that are double in size when you have 2 of that carbon. And so those are going to be our aromatic carbons, right? 4 and 7 are going to be probably these carbons here, that are the ones that are symmetrical with each other. So with that, we still have 8, 9, 10, 11, 12. We know that 10, 11, 12 are going to be our propyl group because those are just normal, plain old, regular carbons. What about 8 and 9? What shows up around 80? And keep in mind, we still have this 2 IHD left. And we don't have any other, it doesn't seem like we have any other carbonyls either.
Would there be a triple bond?
Because we don't see anything else in carbon NMR. What would give us the IHD of 2 that would put something around 80 or so?
Would there be a triple bond?
Indeed, a triple bond somewhere. So, probably have a triple bond here. One sec, I've got a phone call. One sec, I'll be right back. I'm gonna pause the recording too, real quick. Okay, so we've got an alkene maybe. Probably is indicated because we have that carbon NMR peak around 80, and we have one that says drastically shielded, which means, again, we would expect it to be higher. So that peak at 40 is probably the other one, because we would expect that should be higher than 40. It's usually between 50 and 100. And then we also know that we've got the 2.5 on Proton Nmr also is pretty indicative of something next to a triple bond carbon, right? So this is the fun part. We have so much to put together here. With this, we can probably say, based on what we have in the rest of our molecule, that we've got this propyl group that's next to the alkyne. How do we know that? Because this was 2.5 ppm, and we had no other H neighbors. Right? We know we had these 2 H's. This was a triplet. right? We had a triplet there, and there were no other H neighbors. So a triple bonded carbon would make sense, because the triple bond carbon does not have any hydrogens there. And and again, remember with IR, we're not going to see an internal triple bond, so we're not really worried about that. Let's see, any other evidence? No, it's really just the carbon NMR there. So, with that, we now have 2 more carbons taken care of. So we've got our C double bond O, and we've got our triple bond C that takes care of all of our carbons. We've taken care of now our IHD, that's left with 2, so we just have one more thing in this molecule to deal with. And it's that second oxygen. And this is going to kind of be the pain. So where might we expect this oxygen to be? We have now our kind of options for the carbonyl. I'm going to say that's probably the left one, because we found our propyl group is probably going to work nicely with that alkyne. So if we kind of work with that assumption, if we do that, we've got now our triple bond propyl group. We have to put this mystery oxygen somewhere. And so where the heck are we going to put this? We know it's not an alcohol. We know it's not another carbonyl. So that means it has to be an ether. Or it could be an ester, right? So we have a couple of places to try and put it. And we're going to see, kind of with our options, what might make the best sense. So with this oxygen, we can maybe try putting it up here. We could maybe try putting it next to the alkene directly. We could try, let me draw the rest of the molecule. We could try putting it on the other side. And those are kind of the only places we can put it. So we've got 3 options. The reason, by the way, we can't put it the other side of the alkyne is because then we would not see 2.5, we would see about 3.7 or so as our chemical shift. So it's going to be one of these 3.
Hey, Professor. So on your exam, are we going to be expected to, I guess, solve problems of this complexity, or...
I'm just trying to get a home.
Yeah, go ahead.
So on your exam, are we going to be expected to, I guess, solve problems of this complexity?
No, definitely not. No. C14, like, are you kidding me? No. And if you can see on this exam, she only has this one,
okay.
one NMR problem. So, like, you have 2. So imagine yours cut in half with the difficulty.
And this will be saved, right, in Canvas, too.
Instead. Yeah, because this is way too complex. Because, as you see, we've spent an hour on this.
Thank you.
Yeah. So,
and this will be saved, right, in Canvas, too.
Yes. I will upload this video as well as the notes.
All right, thank you.
So, yeah, let's now try and piece this together. I have one more piece of data that I may or may not have covered in the videos, but again, if I forgot that, that's a hint to you. There is, on carbon NMR, if something shows up at about 160, that is pretty strong evidence of an oxygen directly connected to a benzene. And so if we take a look at, and that's again something Mrs. O really likes to go on. So if we work with that, we see carbon number 2 on the carbon NMR is just about 160. Which again is strong indicator that we have an oxygen next to a benzene directly. So that will eliminate one of our structures. And again, if you somehow had this super nasty problem and it came down to putting this oxygen somewhere, that is the smallest number of points, kind of making the distinction between these 3. So let's keep going here. So, which do we think it's going to be? We have, oh wait, we can identify it. And in fact, we already know the answer. We don't have an ester in this molecule. We have a ketone, right? We do not have an ester. If we had an ester, we would not see a peak at 200 in our carbon NMR. So, in fact, both of these can be eliminated. And so this must be the answer. As nasty of a structure as it is. We had a ketone. We did not have an ester. The two left molecules are esters. And so we know we had a ketone. Yikes. What a pain. Wow. There's one more thing that I want us to do that you're going to want to do on the exam as well, which is now that you have the structure, correlate it with the spectra. So, like, now that you've deduced the structure, although this was, again, a very difficult example, I just wanted to do something that we hadn't seen before, and clearly we're in over our heads, but that's okay. If we want, we should correlate all these A through H peaks with our NMR as a way of double-checking, as well as showing to me that you've, like, the work that you've put into this. So if we do that, let's kind of take our structure, massive structure it is. I'm going to just draw it on the side because that's going to be easier. We have our benzene. We have our ketone, and then the double bond. All right. I'm going to just draw one of each of our hydrogens that are unique in this molecule, because we need to label them A through F. So, which one are we going to label as A? Which of these do we think will be hydrogen A? Remember, A is our highest chemical shift there. There are two hydrogens that are labeled as A. Remember, I'm only drawing in one of each type just because, fine, we'll draw them all in. I just wanted to be lazy. Okay. Which hydrogens will be A?
Hydrogen and benzyl.
We know we have two of them, right, from the integration. So, which hydrogens are A?
Top one. Hydrogen and benzyl.
Mm-hmm. Which side, though?
Top one.
These two? I would disagree with that only because those two hydrogens are not equivalent to each other. They're equivalent on the other side. Like, this one is equivalent to that one, and on the same on the other side because of the symmetry. What makes something go downfield?
Less shielding.
Why would we see something at a higher number on the parts per million?
Less shielding.
Yeah, less shielding. So that means, remember that shielding is done by electrons. So something that has less shielding is going to have its electrons kind of taken away. So on which side of this benzene do we think are we more likely to take away electrons? Do we remember our kind of electron donating and electron withdrawing groups from, what would that be, acids and bases, I guess? Let's have a look here. Right side, I agree. So carbonyls are electron withdrawing, and oxygens are electron donating. So we're going to expect that the more de-shielded hydrogen should be on the right side, closer to that carbonyl, closer to the C double bond O. So that means that, no, sorry, that's not B. Which is the other aromatic C. The other ones should be HC then, the lower ones. Again, because it's higher to closer to the carbonyl. Which means more de-shielded. which means higher ppm. Okay, so we've got our aromatics out of the way. And we did identify HB earlier, right? We identified it as this one on the alkene. And we see that it's super high up, again, because of that ketone nearby that one of you pointed out. So with D and E, we didn't quite figure them out. What do we think, now looking at the structure, might be help us identify D versus E? And we can kind of also look at the splitting too, right? Like between D and E, we see that of these doublets of doublets, like one set of doublets is farther apart than the other, right? Like D has a farther spacing than E does. So would that help us identify which one is which? I would agree that D is indeed the lower left. So Matt had, again, written that in a message. So I would agree that this is D and this is E. The reasons for which is because, again, if we take a look at that splitting, or I'm sorry, the coupling constants, 17 versus 12, 17 is bigger. So we're expecting that to be a farther apart doublet of doublets, right? So D is farther apart than E is, but we also see that D is closer to that carbonyl, right? Like we can see that the carbonyl is closer on D, and so we expect D to be a little bit more downfield. So we do see that as well. So normally geminal ones you'll see very close together, but this D is close to the carbonyl there. Okay, so for those two reasons, that's why D should be that left one, and then E will be the right. And then thankfully we already figured out the others, right? We know it's just FGH going down the line. That H was the farthest away, the terminal methyl, and we already worked through that part. So that's something you'll be doing on your exam as well. So you'll be taking the peaks, and once you have your final structure, showing me which one is the hydrogen A, HB, HC, all that fun stuff. All right, any questions on this kind of correlating the spectrum with the structure? We should do the same thing for carbon, although because there are so many clustered aromatic ones, we'll be a little gentler about that, but we'll still we should still do this because, again, you'll want to do it on your exam. So, if we draw out our structure, again, this is, how we're going to kind of double check our answer is by making sure our spectrum correlates with our structure. We have this, and then so of all these carbons, we have apparently 12 of them to label. We already have 4 and 7 as kind of ones we've already kind of talked about, right? Those have to be our aromatic ones because those are the ones that are connected by symmetry. I gave you that kind of hint. So again, we'll work with the same idea that 4 is closer to the carbonyl than 7 is. So these are probably carbons 4 on that side and 7 on the other. Right? We know that 1 is going to be our ketone. We saw that for sure. And then 2 is the one that's connected to the oxygen directly. So we're able to at least get a couple of these out. We have 3, 5, and 6 left that are kind of tough. Right now I would not expect you to be able to distinguish. We would probably say 3 is this one because it's closer to the carbonyl. And then 5 and 6, you know, I'm sorry. Which one are... Oh, because it's next to the other one. So, 6 is a triplet. That's bizarre. Why do we have that? Huh, weird. Okay. Well, we're going to see either 5 or 6 here. Probably 5, given the fact that 6 is a triplet. That's not something we have to worry about with our spectra, because we're not doing hydrogen-coupled splitting on carbon NMR. What else do we have? We've got 8 and 9. And we've got 10, 11, 12. So with this, we're probably going to see that 8 and 9 should be our triple bond, right? And given that one of them is next to an oxygen, that's probably the one that's boosted up a bit, right? So that could be number 8 then. We've got number 9, which is also part of our triple bond. And then we have 10, 11, and 12 going down the line. I don't... Oh, that's where 6 is. Duh. Okay, sorry. I'd missed that carbon. That's actually probably one of these 3 and 5. That's probably closer to 3. Again, I'm not going to expect you to distinguish between these on that regard, and then this one will be 6. That 3, 5, and 6, I wouldn't worry about too much. 7 and 4, yes, you should be able to kind of work with. 1, absolutely. For sure, be able to recognize. And then 8 through 12, for sure. So, sorry, I had missed a carbon, and I was just like, where the heck is this supposed to end up? So,
what type of conceptual question are you going to take us for?
Fun stuff, yeah?
IR, NMR, or some sort of this test? Usual prof, sir.
Mm-hmm.
What type of conceptual question are you going to take us for IR, NMR, or some sort of this test?
If we take a look at the breakdown, we have structure elucidation times 2. That means 2 of these spectral sets.
Thank you.
We have a splitting tree. We have a radical reaction product ratio, and then we have radical mechanisms. Do you see any conceptual questions on there?
Thank you.
Yes. Well, I mean, a splitting tree is conceptual, right? So that's kind of your answer. So yeah, I'm not going to ask you how an NMR works or how an IR works, or give you a set and say build me an IR. That'd be fun. Sorry, Matt had a question as well. Typically, no, this is usually not the hardest exam. Exam 2 is usually the hardest for students. That said, Mrs. O's is quite terrible. How do we do a splitting type of question? Sure, let's do that for this one. Let's take a look at these protons and see how we got those splitting patterns. Okay. Right now, whatever, I'm just going to label these B, what is it, B, D, and E? Yeah. If we wanted to construct a splitting tree for these, we would just need to know kind of the relative J values. Why don't we do one for, why don't we do each of them just because? Actually, yeah, we'll do that. So if we want to do a splitting tree for HB, we want to look at the relationships it has to neighbor hydrogens. It has no hydrogens on the left. We have 2 hydrogens on its right. I guess in this case they're down, but whatever. We have a cis one, right? And then we also have a trans double bond. Remember that the J values for these are about 12 and 17. I do not need you to know the actual numbers, but I do need you to know that a trans double bond, or a trans relationship between the hydrogens, is bigger than a cis relationship to the hydrogens. Alright, because that part I want you to know, but I don't need you to memorize the numbers. Okay, so when we're taking a look at that, we always want to do the biggest splitting first. So if we start, we have our signal. That's in the middle, original signal. And we're going to split it by, first, our biggest one, which is 17. And we have to say how many hydrogens at 17 hertz is this going to be split by. It's just one hydrogen, right? There's only one hydrogen that's in the trans double bond, or trans relationship to HB. right? So we're going to need to split our original signal by what we would say is 17 hertz, thereabouts. All right, so if that were it, this would be a doublet. But we have another splitting to do. We always want to do biggest splitting first and then go smaller and smaller. So our next splitting, the other neighboring hydrogen that HB sees is HE. And HE has a J value of about 12 or so. So we're going to have to split each of these peaks now by about 12. And so it's just, I mean, it's not to scale, of course, but we would expect, okay, it's a little bit less than the 17. Okay, and then so we've now got 4 signals here that have been split each by about 12. I don't need you to write these numbers necessarily, but I would like you to say, like, this one would be, we would say J, B, D. Just indicate which one you're doing the splitting for. So that's the splitting that HB and HD do to each other. And then this one will be JBE. That's the splitting between hydrogens B and hydrogen E. And if we do that, we see that we had originally kind of 100% to start. We split that. So each of these was 50. And then we split both of those. That's 25 each. So we expect equal ratios of our intensity of a doublet of doublets. Right? So this is not a quartet. Remember, quartets have different ratios between the way it's a 1-3-3-1 ratio, not 1-1-1-1. 1-1-1-1 is a doublet of doublets. And we say that this is, it's split it into a doublet. And this split it into a second doublet. And so that's how we end up with the doublet of doublets. And so for this, you'd say that the multiplicity you would indicate as a doublet of doublets. And then let's just do one of the others. Why don't we look at HE? Why not? If we look at HE instead, HE sees 2 hydrogens. It sees B and D. So we would expect that we would have our 2 constants. Again, you don't need to memorize these numbers, but they're about 12 and 2, respectively. Because we have the cis relationship and then we have the geminal relationship between them. So if we do this, we've got our signal. We want to split it first by 12. Again, there's not really a scale here, but about 12. We would end up splitting those. And this is JBE here. We're splitting that. And then we need to split JDE, which is a very small one. And so we will end up with our peaks like that. Over here is JDE, so very small compared to JBE. And again, if we were to look at the ratios of each peak, we'd say, okay, well, it's 50-50 then, and then each of these gets split into 25. Again, you have that 1-to-1-to-1-to-1 ratio. And so again, this is a doublet of doublets, but we can see that the peaks are much closer together, which is why if we actually look at the spectrum, HE and HD kind of have these very, very fine splitting on them. And that's because the geminal coupling constant is so small as a result. So this is also a doublet of doublets. Or we would expect it to be. Alright, so that's kind of what they look like. If you look at question, does she have a splitting tree on this one? Yeah, 6 is a coupling constant question. And oh gosh, look at these molecules. Aren't you so glad you don't have her? At least for this exam. So you can see some examples, and if you take a look at some of the other exams, like if you take a look at the spectroscopy only exams, you should see some splitting trees as well for some of these things. Okay, so you'll be able to get some practice on those, and of course there are thankfully keys available for these, so you'll see those. Oops. So that's what they'll look like. It's basically like, here's a molecule, here's a hydrogen I'm interested in, show me the splitting tree for this particular one. And that would be it. And then you just draw something like this, and you would then tell me, it's a doublet of doublets. Just remember as well, you've got to split it as many times as there are hydrogens, if that makes sense. So here, let's just do something super quick. Let's take a look at an ethyl group. I don't know, let's say it's got a ketone or something, so there's no other hydrogens nearby. If we wanted to do the splitting tree for HA, we need to look at the coupling constants. So we've got JAB, and that's the only one we have, but we've got 3 of them, right? There are 3 different HBs that HA can interact with. HA does not see the other HA because they are equivalent to each other. Remember, on a single bonded carbon, the hydrogens are the same, so we don't need to worry about them. It's only on neighboring ones. So if we want to look at a splitting tree for HA, we know it's going to be a quartet, right? It's got 3 neighbors, but if we want to do the tree, we need to draw it out. So if we do so, we have our whatever JAB happens to be. It's going to be pretty small because it's just an alkane. If we do that, we split it up. And then because the coupling constants are the same, JAB is the same for each one, we have to split again. We have to split 3 times. And notice that because we already split it in half, and then we split in half again, we do see that there is this overlap. And so we will see that happening. And then we're going to split it one more time, because we have 3 hydrogens, or 3 JABs we need to put in here. And so we again want to kind of make them fairly even. My drawings are, as always, terrible, but that's okay. So this is also JAB. Each peak needs to be split by our coupling constant. So we are left with these purple peaks, which are the where the splitting has ended up. And if we look here, we had 100 going in. The first time we split it, half goes to each side. And then each of those we split, putting now actually 50 on this middle one, because it gets 25 from each side. And then splitting them again, 12 and a half, 12 and a half. And then this side is 50 over 2, so that's 25. 50 over 2 is 25, 12 and a half, 12 and a half. These are just the relative sizes. So we see a 12 and a half to 37 and a half to 37 and a half to 12 and a half, which if we reduce is 1, 2, 3 to 3 to 1. And so we would expect that we would get, in this case, that's so embarrassing, quartet. There we go. All right, so that is what it looks like for just a regular carbon. So you just need to split it as many hydrogens as there are there of that type. So because this is split by the first B, the second one, and then the third one. And then so we'll end up with these ratios, and then we end up with our 1 to 3 to 3 to 1 nice quartet there that we see. Okay, so that's what a splitting tree would look like for that. All right.
Excuse me, Professor.
Other questions?
Can you solve a question for bromination ratios? One of the question that you briefly solve one question on lecture. Yes, please. Excuse me, Professor.
Yeah.
Can you solve a question for bromination ratios? One of the
Bromination. Oh, okay, I know what you're saying.
Solve one question on lecture. Yes.
Sure. Let me see if we have one in.
Yeah, that should be fine, but I chose bromination because it is more
chlorination or
selective.
bromination. The only thing that's different is the numbers, but would that be okay if we did chlorination?
Yeah, that should be fine.
Okay.
But, I chose bromination because it is more selective.
It is more selective, so the only thing is they'll just get bigger numbers out of the bromination. In that case, let's see if we can't find an example on one of her exams that we can just look at the question and go for it. So this is these are chlorination. Goodness gracious! Let's find one that has bromination. Oops. Mass. I just want to do this so we don't have to actually like come up with a problem. Mechanisms. Okay. Oh no, this is the same as the one on the worksheet. I think we're just gonna have to do chlorination because it really is the same. It's just you just have different numbers to work with. So you just have different ratios. Remember that it's the numbers. I'm going to provide them to you anyway. So like the 1600 and the 80, like you don't need to memorize them. So for chlorine, we'll have them as well. So if we take a look at, I'm looking now at the Fall 17 exam. Question number 3. And I'll read it. It is photochemical chlorination of 3-ethylpentane afforded 3 products with relative reactivity of primary, secondary, and tertiary hydrogens reported as the following. 2, I'm going to put these out. Primary, secondary, tertiary. We had 2, 2.5, and 3, respectively. What we needed to do was go ahead and figure out the distribution of the products. So we have 3-ethylpentane, so that's the first thing we need to do is draw the molecule. So this is 3-ethylpentane, and we have the ratios, or the what we're expecting to see with the products. So the reactivity here is given to us, and I will be giving that to you because it's useless to memorize.
9.
So if we do that, what we want to do is count how many of each type of hydrogen we have. So how many primary hydrogens do we have in this molecule? And you tell me.
9. 6.
Right. Each of these terminal carbons has 3 hydrogens. Those are our primary ones. We've got 3 of them there here in purple. Great. How many secondary do we have?
6.
6. And I'll put those in black, just so everybody can see them. And then how about the tertiary?
Just 1.
1 hydrogen. And that'll be blue. Great. So with this, what we want to do is simply multiply the reactivity by the number of hydrogens that we have. And then from that, we're going to be able to determine kind of the product ratios. So 2 times 9 will be 18. 2.5 times 6 is 15. Yes, 15. And then 3 times 1, of course, is 3. So in order to find out the percentage of each one, we simply need to add everything together. So 18 plus 15 plus 3 is going to be 36. And so as a result, the total is 36. So the percentages, 18 over 36 will be 50%. 15 over 36 is a number I do not know immediately. 3 over... 5 over 12, which is what? And then 3 over 36, which is 1/9, which is going to be 9%? No. I don't know.
0.08.
Do the math for me. What is 15 over 36?
43. .08.
15 or 3?
43.
Okay, so that's 8%. Okay, and then this must be 42% then by just subtraction. So that's how we're going to get it. We just simply need to figure out how many of each we get, and then just combine them and see the percentages of each one. So 50% of the products will be on the purple hydrogen, will be a primary chlorine. We'll have the 42% will be on the secondary position, and 8% will be on the tertiary. And so in this case, the major product will be the primary one. If we wanted to do bromination, we could do the same problem, right? Instead, our reactivities are just different. We see that a primary would be about 1. We'd say this is about 80 and 1600 are roughly the selectivities for bromination instead. And we would do exactly the same thing. So we say we've got 9 hydrogens, we've got 6 hydrogens and 1 hydrogen. So we have 1600, we've got 480, and then we've got 9. Adding that all up, we have 2089. If I know how to do math properly. I think that's correct. So for the percentages, we would just do the same thing. All of these numbers divided by the total, and then make it a percent. And so if you wouldn't mind calculating those for me.
For the first one is 0043. For the first one is 0043.
Okay, so 0.23. Okay, keep going. I'm multiplying by 100, so it's a percent. Just that's why I had to think about it.
0.76.
What about the next one?
0.23.
Okay. And then the last one?
0.76.
Okay, so then this is our rough, of course we'd have sig figs and all that nonsense as well. Actually, forget it. We don't need to worry about sig figs. We see that this, it almost adds up to 100. There's just some decimals and rounding and stuff. But this would be the distribution for bromination. We would see the major product would be the tertiary one. And as we know, bromination is much more selective. So we would see in this case, 76% of our products would be the tertiary, and then we would see smaller amounts of the other two.
Can I ask another question?
So that's the only difference between bromination and chlorination is these numbers.
I want to know, we can get our favorite product either on propagation and termination process, both of them? Can I ask another question, Professor?
Yeah, go ahead.
I want to know, we can get our favorite product either on propagation and termination process, both of them?
You can, but it's much more common to get it through propagation. Termination usually is a very minor amount of the total process, simply because it ends up slowing the reaction down. So with propagation, you keep things moving. And so it's usually much more useful. And so most people will show the formation of the desired product in the propagation step. because termination, you can get all sorts of weird things. You can get just like if you're trying to couple, two bromobutane or something, you're trying to make that. Like, if you end up doing this, yeah, your major product will be putting the bromine on one of the secondary positions, right? Ideally, yes, you will show this in propagation, because termination, you can get all sorts of weird things happen. Like, you could have two of these radicals coming together, forming some weird product. You typically will not show the bromine radical in this step. So, like, you'd get some weird products. Oops. And, like, things like this usually happen in termination. That's where you get your side products. So, best to show it in propagation. Okay?
Thank you.
Yeah, termination, you get all of them. You get your original bromine back, and you also will get your product, but just not useful. And in fact, I think on the exam I have asked you just not to show termination steps, so we'll make it super easy. All right, by the way, make sure when you are drawing the arrows for the mechanisms for radicals that you use these the fish hooks. Like, don't use regular arrows, because regular arrows means 2 electrons. You have to use the half arrows. So make sure that you do that. So there's plenty of examples of mechanisms in the that worksheet. So make sure you're doing your mechanisms just like those. All right, so you can see that how things are coming together. By the way, also, although I didn't do it on the worksheet necessarily, make sure you know, like, for example, this would be a coupling, right? We're taking 2 of the radicals and coupling them together. We want to be able to identify this step, kind of the very first one, as homolytic cleavage. Make sure you know these names. Right? Or say, for example, now that we've got the bromine, and we're going to go ahead and react it, this is, remember, a hydrogen abstraction. So make sure you know all these names. The other 2, by the way, I'll just write them out. There's halogen abstraction and coupling. Remember that coupling is... so homolytic cleavage is in your initiation step. The abstractions are in propagation, and then coupling is in termination. So that's another, I guess, hint I have for you. These ones are both in propagation. Homolytic cleavage is in initiation only. And then coupling is in termination. Okay, so you will be asked to name the types of reactions.
Sir, what about the addition of pi bond?
Okay, so don't forget those. I'm gonna just put this as a bubble, just so it's clear. All right.
Sir, what about the addition of pi bond?
We don't have those in these radicals, at least. Addition to pi bonds is something that we'll see, but I have not put that in your mechanism. So elimination and addition, we'll worry about those later on. So. At least in these halogen reactions of alkanes.
I had a question on that handout.
There are no
on page
bonds,
7,
so
it's number 1, and you ranked the most to least likely reaction. Could you go over and explain your logic as to why
Professor, I had a question
letter B
on
was
that
the
handout.
least?
On page 7, it's number 1, and you ranked the most to least likely reaction. Could you go over and explain your logic as to why letter B was the least.
Okay, let me see here. Where is this? Okay, so number 1 that's on page 70, of course. That makes total sense.
I have,
was
I wrote it down the
Okay.
answers, but
So
I don't have
why
the
is it
key
most to least?
exactly.
So what we want to do here is evaluate the stability of our intermediates. And so, do you have the key open out of curiosity with this?
I wrote it down the answers,
Okay.
but I don't have the key.
Sure, okay. Then in that case, I know what I can do. I probably still have it open here. Ta-da! Okay. Yes. Alright, so we're on page 7. Sorry, it's super hard for me to write on these, that's why it's a little bit messier. But if we take a look at the radicals that are involved, let's use just green here. These are the radicals that are going to be our intermediates. So how we determine most, least, and all that is we're looking at the stability of these radicals. So really, it's not really asking us kind of what's the it is asking us what's the product distribution, but what that really means is what's the more stable intermediate. And so with this, we want to compare these three. And so what we're looking at, remember that with stability of radicals is identical to that of carbocations. And so what we want to do is let's label all of these. That top one, boxed in green, that one is a secondary
Okay. Yeah, I think I got it. So
allylic radical.
is it?
We see that because it's on a secondary carbon,
and
and it's also got a double bond 1 carbon away. So that is a secondary allylic radical. So far, so good?
Okay, yeah, I think I got it. So,
Yeah, go for it.
but then doesn't the least and middle both have double bonds?
They do, but this is secondary that's not allylic. Because you see here, like, the neighboring carbons are these two. For it to be allylic, it has to have a neighboring carbon that is got the double bond. Because that middle one can't resonate. There's no way for that one to resonate. But the allylic ones can resonate, and that's what stabilizes them. So in both situations here, the carbons that are adjacent to the
Okay,
radicals,
I think I understand. It's just the resonance.
in the first and last
I think I was
are
confused
both
because it looked like the
so they're
chlorine was
able
on
to
the
resonate because they
primary
have
versus like the secondary.
those
So I was
double bonds on adjacent carbons.
Okay, I think I understand. It's just the resonance.
Yeah.
I think I was confused because it looked like the chlorine was on the primary versus like the secondary.
Right. Yep, that's the thing, is we have to consider benzylic and allylic things first, and then we worry about primary, secondary.
So on the test, will we need to rank these?
And so secondary
Or
allylic
is
is
it
our
more
most
just like
stable,
common knowledge?
then primary allylic, and then the secondary regular will be the least stable. And so that's why we will have that, say, the product distribution as such.
Okay. So on the test, will we need to rank these? Or is it more just like common knowledge?
So if I ask you, then yes, you'll need to. As much of an answer as that is.
Okay.
Yeah. Can't reveal too much about it, right? So, but like you can also see some similar exam questions, like if you take a look at, for example, the fall 2017 question 1. We'll have kind of ranking radical stability, so you'll see some similar things there. It's really exactly identical to carbocations, so we're looking at benzylic being the most stable, then allylic, and then regular carbons, and then in all three of those, we also look at tertiary, secondary, primary, in that order. So, but again, look at the kind of class of it first. So benzylic first, tertiary benzylic better than secondary benzylic, better than primary benzylic, all of those better than allylic. And then within allylic, 3-2-1, and then after allylic is his regular ones, and then again, then we look at 3-2-1.
I think this has been really useful. Thank you.
Yeah, this helped out quite a bit.
Are your brains sufficiently fried? I mean, they've already been fried, I guess, haven't they? But
I think this has been really useful. Thank you.
good.
Yeah, this helped out quite a bit.
Awesome. All right, well, I will go ahead and I'm going to stop the recording.